Welcome to the Space News webinar, Space Loves AI. I'm Debra Werner, Silicon Valley correspondent for Space News and moderator of our discussion. There's no denying AI's impact in the space sector, from fusing Earth imagery data sets to designing spacecraft and space missions. The impact of AI is already important. Most of that work, though, is happening on the ground for the moment. Our discussion today focuses on space-based AI, which presents unique opportunities as well as unique challenges. We've assembled a great panel to discuss the topic over the next hour. Today's webinar is sponsored by Redwire. We'll begin with a brief video from Redwire.
Beyond the edges of Earth's atmosphere, there is an advanced network of space technology, serving as an orbital watchtower to protect our nation and ensure the safety of our daily lives. But as the threat to our global security grows, so must our vigilance and urgency. Redwire, we are honored to support those charged with defending our nation and its freedom to operate in space. Together, we are rapidly deploying solutions for warfighter communications that speed the exchange of information and shorten decision-making chains. We are building resilient mission architectures to mitigate threats and ensure dominance throughout space. And with our capabilities for space domain awareness, we help ensure the safety, security, and sustainability of our nation's activities in an increasingly contested environment. In the face of the unknown, we stand ready to serve the brave men and women who act as our guardians and using cutting-edge technology are protecting our future. Together, we defend above.
For those of you tuning in live to the discussion, you're welcome to submit questions using the chat button on your screen. Space News editor Brian Berger will be keeping an eye on the questions and help bring those into the discussion. Now for introductions. I'd like to ask the panelists, Al, Mike, and Simone, please introduce yourselves and your organizations. Magnestar CEO Jacqueline Good was unable to join us at the last minute.
Thanks, Deborah. This is Al Tadros. Hopefully you can hear me okay. It's a pleasure to be here on this really important and timely topic. Redwire is a space infrastructure company that has been deploying critical capabilities with our partners and customers for 4 years as a Redwire company, but with legacy companies spanning back 50 plus years in the space industry, developing and deploying capabilities ranging from solar power generation to avionics and cameras. So I'm happy to be here calling in from Silicon Valley, where I'm based out of, and happy to join the discussion.
Thank you. Mike?
Yeah, so my name is Mike Nemerouf. I work at the Aerospace Corporation. The Aerospace Corporation is a federally funded research and development center. So for those of you that are not aware of what that means, an FFRDC, it's essentially came out of the Manhattan Project, which hopefully many of you have seen Oppenheimer. So it may be clearing some cobwebs out there, but it was essentially a way to keep academics and researchers aligned to national security needs, so that in matters of national defense, there would be readily available sort of research workforce to help the nation get after defending itself. Aerospace Corporation primarily supports the entire space enterprise, so from ground systems to user equipment like GPS user equipment, to spacecrafts and launch vehicles. And we are a systems engineering firm. So we are there to ensure that what the government tries to acquire gets delivered on cost and on schedule, and delivers the capabilities that are needed to defend the nation. And I'm very glad to be here, so I appreciate the invite, and I appreciate being on this panel with these esteemed panelists.
Thank you. Happy to have you here. Simone, tell us about
Yes.
Berger.
Yeah, thank you very much for the invitation. It's a pleasure for me to be here. First, a little bit about me. I'm a professor of aeronautics and astronautics at Stanford University, and also a professor of geophysics by courtesy. And my research tries to enable future distributed space systems. So these are systems made of 2 or more agents in space that are intended to accomplish objectives that are otherwise impossible, very difficult to achieve by a single monolithic spacecraft. So I have multiple roles within Stanford University and outside Stanford University. Within Stanford, I'm the director of the Space Rendezvous Lab, which is my research laboratory. But I'm also the director of CESAR, a new research center we have just founded with the sponsorship of space industry, including Redwire and Blue Origin. CESAR stands for Center of Aerospace Autonomy Research. And the goal of CESAR is to endow space vehicles with autonomous reasoning capabilities through research at the intersection of machine learning, artificial intelligence, and spacecraft controls. Yeah, thank you very much.
Thank you. So I'd like to begin the discussion by talking about the opportunities that AI and machine learning offer, especially for space-based applications. As I mentioned in the introduction, much of the data fusion and data analysis is now occurring on the ground. Let's start with you, Al. Where do you see this going in terms of the next few years and the opportunities?
Yeah, well, it's actually a very exciting application of artificial intelligence. And actually, my background is guidance, navigation, and control, GNC, and attitude and orbital control, which has really delved into a control system design for complex and self-contained spacecraft for decades, looking at increased level of autonomy, reliability, operational capability. So artificial intelligence is the latest addition to what might be called classical controls approaches for guidance, navigation, and control, fundamental operating requirement for satellites and space systems. Even more so, capabilities that require machine vision, satellites that are using cameras for rendezvous and proximity operations, 2 satellites approaching each other and maneuvering around each other, and then approaching to dock or berth. Those kind of capabilities are critically important and dependent on increased level of autonomy. And then as we go to the lunar surface, obstacle detection, navigation for vehicles. We all saw, or many of us saw, the lunar terrain vehicle contracts that were awarded just a month ago or so. And robotic vehicles moving around the lunar surface are great examples of where AI could and advanced autonomy can be applied. There's a whole plethora. Space systems are ripe with opportunities because of their nature of being complex, self-contained, and oftentimes depend on timely decision-making and complex decision-making at the level of humans or even beyond in order to operate safely. So that's just a glimpse into where the applications exist.
Simone, anything to add?
Yes, of course. So we were motivated to create this research center at Stanford, which is first in the field, by the desire to unlock the potential of artificial intelligence and machine learning for space applications. So where does this potential lie? Well, if we go a little bit closer to the algorithms, we are talking about two features that share artificial intelligence algorithms. One is the universal approximation capability, and second, the generative capabilities of AI algorithms. So these two features are leading to advances which can be classified either as enhancing and enabling. So let me give you a few examples. In autonomous spaceborne navigation, in my mind, and considering my long-term vision, we are a little bit in a primitive stage whereby we rely largely on ground assets, not only through the deep space network, for example, or a network of ground stations on the ground, but even GPS. I mean, it's completely managed from the ground for navigation of our satellites in lower orbit. Now, where does AI factor in? I mean, the universal approximation capabilities of AI are able to digest and learn large amount of data. For example, the space object catalog, more than tens of thousands of objects can be learned by an artificial intelligence model. And this could be used for autonomous collision avoidance in orbit for improved sustainability and space situational awareness. Or an artificial intelligence model can be used to learn from a data set of a large number of spacecraft how to recover the 3D model of a spacecraft from single images. And so that's, for example, an enabling capability, not just enhancing, because classical methods are not able to recover the 3D model of a spacecraft from a single monocular image, for example. And this is vital for activities such as rendezvous, proximity operation, docking, capture, and debris removal. So for characterization of debris. But thinking even longer term, AI as the space navigator, a space vehicle so that can be either on the surface of a planet, of a moon, or in orbit, can take images of the surroundings and determine through an AI model where it is very quickly. So we're talking really about a plethora of opportunities that then go into, besides the technology, into the data processing for remote sensing and science. AI can enable processing at the edge and identify pattern and extract intelligence information or information of interest from measurements that are obtained by satellites, either autonomously on board or either on the ground, given the huge amount of remote sensing data that we are collecting today through constellations and mega constellations, all the way to digital twinning. So the universal approximation capability of AI might enable the creation of digital twins of space vehicles to identify early on failures of equipments. This is the predictive maintenance capability that AI could unlock. Robotics. So AI-driven robots will be essential, not only as companions of humans for space exploration, but to substitute humans in activities that are too dangerous or difficult to accomplish by an astronaut. Finally, scaling to multiple agents. Classical methods have a very hard time coordinating a large amount of agents and solving multi-objective constrained optimization problem on board involving multiple assets. And that's where the universal approximation capability of AI models can be advantageous because they can guess very quickly a solution to that optimization problem and then feed into potentially classical control algorithms that then needs less iteration to converge and they can improve their performance.
Great. Mike, anything to add there about these opportunities?
Yeah, and just a little more background about me is I'm a former Army intelligence specialist. So I spent about 10 years in the Army, deployed to Iraq and Afghanistan. So to me, the promise is using AI as a tool to enable warfighters is one of the biggest promises out there. And as I started to learn more about the space enterprise and what Guardians need to do on a day-to-day basis, I gained a real appreciation for how AI, the promise of AI on board to help them be more effective in their job. And one way I like to think about it, so in the near term, it's enabling Guardians and warfighters. And in the longer term, I'll talk about sort of making better use of all the hardware the government's already put up in space. But if you think about a spacecraft, let's talk about low Earth orbit, which is, about 400 to 500, between 400 and 1,000 kilometers above the Earth. These vehicles are moving at around 4 miles per second. Okay, so they're essentially robots in space. They've got sensors that make observations. They've got telemetry streams, which is essentially different ways of monitoring what's happening on board the spacecraft and around the spacecraft. And then we have sensors on the ground that's sort of trying to keep track of where all these different objects are, the tens of thousands of objects that Dr. D'Amico mentioned. So what happens for a Guardian that needs to sort of manage US assets in space is they get down this inundation of data. And it all comes down based off of sensor readings, multiple threads. So you've got maybe pictures, and then you've got pressure sensors and temperature sensors and all these different things. And then you've got observations of the sky, streaks moving quickly back and forth. And they have to, so you're talking about 1,000 kilometers to get the data down to the Guardian. Then the Guardian has to figure out with some advanced tools what's actually going on up in space. Why did we lose communications? Was it a space weather event? Are we having a malfunction on the spacecraft? Is there more malicious intent going on? So you're talking 4 miles per second. Think about how many seconds it takes just to get the data down, leverage the tools necessary to present that information to a Guardian, go through the decision-making process to figure out what's happening, orient them to the problem, and then make a decision, and then command that spacecraft to either avoid a collision or get out of harm's way or whatever the case may be. A lot happens in that timeline. And to be able to use onboard processing to sort of use machine learning's universal approximation function, as Dr. D'Amico mentioned, to make sense on board of what's happening and send down kind of what an operator actually needs to see, with all the details, of course, as backup, that enables faster decision making for the Guardians, and they can handle more of a workload as space becomes more congested and contested, to be frank. So that's one type of application, just making sense of everything that's going on up there when things move so quickly. The other option is, so we've been putting satellite vehicles up in space for 60 years, and aerospace has been a big part of making that successful. supporting the National Reconnaissance Office and the Space Force, formerly Space and Missile Systems Center in the Department of the Air Force. So there's a lot of hardware. There's a lot of sensors. Every sensor is kind of unique to a particular mission set or capability. So one sensor may be like a listener, so it can receive radio signals. And another one might be able to take one type of picture. Another might be able to take another type of picture. And then you may have these on-orbit servicing mechanisms that have a particular type of tool to repair a solar array or whatever the case may be. Imagine a world where you could bring together different satellites and different orbit regimes to accomplish a very particular mission using these multi-objective functions that Dr. D'Amico pointed out, and then return back to their day-to-day life. So now you're getting a lot more capability out of existing hardware and spacecraft without having to throw more hardware up there and continue to congest what's already kind of exploding exponentially in terms of space objects. So those are the two main promises I see.
Yes, we could spend the whole hour talking about these opportunities, but I think it's also important to consider the challenges. Al, you said in a recent conversation, many of them are engineering challenges, thermal challenges, power challenges, radiation, things that you've dealt with in some respect your entire career. But as we get further into space, some of them are a little tricky. The moon's a tricky environment. What do you see as the challenges?
Yeah, I think that as more people are getting involved in space architectures, deploying capabilities in space, there are engineering challenges that have existed since the start here, and you mentioned some of them: the thermal and radiation, even micrometeorite impacts. Right, orbital debris has existed forever. I mean, you could just look at the moon, and its features are based on impacts. That's what we see, and satellites have to survive those. Even at sand grain level impacts, you can detect and see their effects on satellites. So those are all engineering challenges, and that's part of why we as engineers came into the field, because they're some of the most exciting and largest challenges in the engineering field. Unique to AI so as we go further into space and to the moon and to Mars, deep space, there's uniquenesses there. There's latency in communication. There's extreme temperatures. The moon has 2 Earth weeks of sunlight and 2 Earth weeks of darkness. That's its a solar cycle there on the surface, and there's challenges there for generating power, for managing thermal. There's uniquenesses based on that. Those are all things that we have engineers that can take on and work. Some of the unique challenges of AI, as Dr. D'Amico mentioned, is just the data sets for training algorithms. So collecting sufficient data and practicing and training models on those. Here on Earth, we have a vast amount of data from the social media channels, and for posts, blogs and posts and video channels that are used to train. We need to develop techniques for training, and Dr. D'Amico's mention of Caesar is one example of where that kind of research is heading, is how do we train algorithms uniquely? And those are some of the challenges that I think are exciting for Redwire to work with Stanford and other cohorts to develop solutions for. I'll stop there.
So Simone, is training these algorithms for space applications different from training things for terrestrial applications?
Yes. So many of the things that Al said resonates with me and our research. I'll use my words to very briefly say what are the key challenges of AI for space applications and at the same time answer your question. This panel or this webinar is called or titled Space Loves AI. But actually, space is hard for AI because of 4 reasons, mainly. One, lack of data, either because we don't have the data or because they are not publicly available. 2, remote environment. In contrast with robotics, terrestrial applications, where things can be deployed and can learn from the actual environment where these things are going to operate. Space is not available, it's not at hand here on the ground. Second, space is harsh, and this is what Al said about the survivability of transistors and the qualification of GPUs on spacecraft, and we are at a very early stage to do that. Finally, risk aversity. Space is traditionally very risk averse. We need to meet hard constraints. And this is something that AI algorithms are not so good at. So it's difficult to discipline an AI model so to remain within boundaries that are prescribed by the users. And that's vital for space application, as Mike was saying. How do we deal with collision avoidance? Which is a hard constraint. And so in order to respond to these challenges, what we do is to create surrogate environments on the ground to stimulate our sensors under realistic conditions. And so this is intended to attack the problem of the lack of data, because we can generate this data either through high fidelity simulation or through hardware in the loop testbeds, and try to tackle the remote environment by having this surrogate environment that can be used to certify or verify that an AI model that has been trained on pure synthetic data can meet the requirements on the space simulator. And risk aversity. How do we deal with risk aversity? Well, the recipe that we are proposing and that we are investigating as part of the CSAR Research Center is a fusion between AI, machine learning techniques, and techniques that are more classical, so to say, from optimal estimation and control. Now, AI and machine learning techniques bring advantages because they can explore the solution space globally and provide very quickly a guess for where to go, for where I am, for what is it I'm looking at, but without meeting those hard constraints I was talking about. Now, that guess can be provided to an optimal estimator or to an optimal control scheme, for example, based on convex optimization, based on sequential convex programming, that can enforce rigorously those constraints. And that's the advantage of the classical approach. And then we can do handshaking, and we can close the loop between an artificial neural net and the optimizer, so that the artificial neural net can learn online how to become more robust to the conditions that are encountered in space that were not foreseen or simulated on the ground.
Yes, so these are federated systems with nodes in space and nodes on the ground.
Well, we can see it in multiple ways. Either for a fully autonomous system where we want minimal ground intervention, this whole training is done on the ground so that it's as robust as possible. It is then deployed on the edge, on the satellite, and the model learns on the work. Basically, when faced with new measurements with the actual conditions of space, for example, it was trained in a way where the sun was not producing adverse effects to my vision-based sensor, but then when these adverse effects are seen in orbit, thanks to the pairing with the optimal estimation technique, can learn about this condition and be retrained online. So here I'm talking about a fully autonomous system that can learn how to cope with those challenges online without relying or with minimal intervention from the ground.
Got it. Got it. So, Mike, what do you have to add about the challenges?
So I think Al makes a great point that there's some engineering challenges. One of the ones that Simone D'Amico just pointed out is this online learning. The space qualified AI hardware for training on orbit is just not quite there yet. The power needs and sort of the rad-hearted nature and the size, weight, and power, there's a lot of research being done there, but that is certainly an engineering challenge. I wanted to focus more on one of the components Dr. D'Amico mentioned, which was the risk aversion of space. So it's the human component. And the way I look at AI tools, no matter where you use them, in space or on the ground, is they are a set of tools. Much like construction tools, I would let my 7-year-old operate a screwdriver unsupervised. I would even let my 7-year-old operate a power drill, but I would be standing very close by. I'd either be holding it stable or I'd be right there in case things go off the rails, because I have a certain risk model and I have a certain tolerance for risk when it comes to my child and the thing that he's screwing into the wall, right? So I've already kind of had the mental model is what's the worst that's going to happen? How can I mitigate that effect? Now, I would never let him operate a chainsaw, whether I'm standing there or not. He's 7 years old, he's not going to operate a chainsaw. I would operate a chainsaw, but you know what I'm not going to operate? A crane. You don't want me behind a bulldozer or a crane, trust me. But there's these levels of risks and levels of mitigations that can be put in place if we could accurately articulate the risk and the mitigations to decision makers so they can make an informed decision as to whether or not they're going to tolerate that risk, given the importance of the mission. So with any tools, in the construction analogy, you got tools. So you've got regression models, linear regression, which you could call AI. You got expert systems, which you could call AI. And then you also got large language models, which is like the cranes of the construction analogy. All tools have a place on a construction project, but it all depends on the building materials you're using. It depends on the architecture of the building you're trying to design. And then it also depends on what your risk tolerance is. And what I'm seeing across the space enterprise is the risk tolerance is rising for decision makers. But what we need to do as a community of AI practitioners, between industry, between academia, between FFRDCs and government, is really focus on how are we presenting that risk in an accessible way and associated mitigation strategies so that somebody can actually make an informed decision on whether or not to put AI in space. And to me, that's the human component that it makes AI in space incredibly hard, because even AI in high consequence environments on ground systems, also incredibly challenging to get pushed through unless you've got a very high risk tolerance. And a lot of the work that's come out of Stanford and a lot of other academic institutions, and even the DoD's Chief Digital and Artificial Intelligence Office, the CDAO, they're focusing, building out tooling and methodologies to better articulate that risk and mitigate that risk associated with AI-enabled systems. It hasn't quite reached space-based AI yet, but I'm very excited to see what comes out of this Cesar Center, because they already have a head start on a lot of that.
Yes, you and I had an interesting conversation about guardrails, about implementing AI while ensuring that it doesn't go off the rails. And it seems like that will be an important part of this, constraining the AI.
Yeah. So one of the guardrails in the construction analogy was me standing there holding the drill, right? A guardrail in the space-based AI is what Dr. D'Amico pointed out, which is you have a closed loop control system. You're just seeding that control loop. That's mathematically proven. You understand the bounds of how that control system is going to operate. We just need to understand what are the guardrails necessary for which AI tools and associated applications to effectively mitigate the perceived risk and the real risk associated with space-based AI. And we don't have all the guardrails readily available yet, but there's a lot of really smart people working on them.
Great. Simone, you're an expert on swarms of spacecraft working together. How is AI important there, and what has been happening in that area?
Thank you, Debra, for the question. So very briefly, what are the research pillars that I'm working on to answer your question? So we conceive new mission concepts employing multiple satellites. And that's the first place where AI could help by optimal spacecraft design. These multi-satellite mission concepts that are intended for a number of first-of-its-kind applications in Earth remote sensing, in astronomy and astrophysics, for space logistics. They come with tight requirements. And so this is where we do research on the algorithms, which are the intersection of optimal estimation, optimal control, machine learning, to build the GNC and decision-making stack for these multiple agents in space. We then take these prototype algorithms and validate using robotics and augmented reality. And finally, after they reach a certain maturation level through testing on the ground, we embed them and fly on actual missions. That's our fourth pillar. And I would like to mention the starling mission. Starling is a bird species that like to swarm. It's a NASA managed mission that was launched in July 17th last year. It is now successfully operating in orbit. It's a swarm of 4 6U propulsive CubeSats, basically shoeboxes size, and that is intended to demonstrate the autonomous capability of a swarm to navigate and control its motion in space. On board the swarm, we are demonstrating a new navigation system. This is a distributed optical navigation system whereby the satellites, using optical cameras, they can look at one another, exchange bearing angles obtained from those images, and determine the orbits autonomously, the orbits of these swarming satellites. Now, getting to your question, what is the next step? The next step is scalability. Okay, we are demonstrating this first of its kind technology in low Earth orbit. How do we scale it, for example, to a mega constellation that could become an eye, a distributed eye in space? So a space situational awareness sensor that can take images of the surrounding, conglomerate, get together all those images, and produce a global picture of the space population using all the images from these cameras. And here it comes the crucial role of AI that would be able to execute such a task, not only for a cooperative ensemble of spacecraft that track and monitor the space environment. This is, for example, SpaceX recently contacted us because they have interest in our distributed optical navigation system, and they would like to adapt and scale it up to the Starlink constellation. So that's the Starlink constellation made of 5,000 satellites that could become a space-based situational awareness sensor. But if you swap the story, then you get to these autonomous capabilities of that can be enabled by AI, where a single observer looking around, for example, a fisheye camera, can track a large number of resident space objects, not only the stars and not only see the Earth and sometimes the moon if it's in Earth orbit, but it can see the resident space objects that are in space. Now, how do we correlate these objects to our knowledge of these objects from the Space Object Catalog that is available on the ground, that is managed by Space Command? And that's where AI can play a key role in doing a concurrent estimation of the orbit of that observer, together with the identification of all these objects that can serve two purposes. One purpose would be an alternative PNT system whereby the observer, by just tracking other objects, can determine its own orbit because there is a priori information about where they are. And second, improve the knowledge about the orbits of these resident space objects. Now, these capabilities are not available today, and it's impossible to process the Space Object Catalog efficiently on board the spacecraft. And that's where a neural net could be trained to learn the Space Object Catalog and help us solve this problem autonomously on board, involving a large number of spacecraft. These are just examples, but.
No, I understand. Let's turn to Brian, because we have a lot of good questions coming in.
Thanks, Deborah. Let's start with one that has a pretty good preamble to it. An attendee from today's webinar asked, the majority of the companies that are offering AI products and solutions to the federal government are not offering anything that is novel. Many of the products and services are not truly AI, but companies are slapping the AI tag on the offerings. How can we ensure the federal government cuts through the AI hype cycle and truly procure AI products and services that are transformational? I think that's a good one for Al. But first of all, do you agree with that characterization? And the second part, the question of ensuring that we separate the hype and have the federal government procure stuff that's truly useful.
Yeah, it's a great question, and all of us are probably hypersensitive to buzz over, all kinds of platforms that doesn't have real substance behind it. I'll tell you it's what, as a CTO at Redwire, that's one of my pet peeves. And the proof of the pudding here is real mission capability, whether it's warfighter capability or business results that can be achieved. So I do have a specific technical metrics, but in general, again, I'll go back to my my education and engineering expertise in GNC. Classical techniques can achieve a certain level of capability. What I'm looking for, and part of our involvement in CSER, is how can we go beyond that? How can we enable sensors, cameras to perform well beyond classical approaches? And we talked about one of those, or Dr. D'Amico mentioned one of those, with a single image or a set of limited set of images and pixels with 2D images. Can we reconstruct a full 3D rendering and then extract the pose, the position and orientation of the client satellite from those images? Those are some challenging things for classical techniques. So there are some metrics that really prove out where do you have capabilities well beyond. To the question, I believe that the government does have that challenge, but with technical expertise and understanding of where the state of the art exists and what true, AI algorithms trained on what models really means and differentiates itself from classical approaches, I think there is a genuine and quantified distinction. Let me also mention that compute power, as Mike and Dr. D'Amico mentioned, compute power is required for a lot of these algorithms, and I'm encouraged by the number of entrants in edge computing that are using, NVIDIA and AMD and other modern processors for space tolerant, radiation tolerant processing. I'm really encouraged by that. In addition to the increased access to space that companies have, yes, the government tends to continue to be risk sensitive and risk averse. However, with the increased access to space, there are a plethora of companies out there and universities and labs that are putting up capabilities on a regular basis that are pushing the envelope in compute power and algorithms. So I believe that we will see a rapid ramp up in true AI capabilities and advanced autonomy capabilities being deployed.
Brian, can I add one point to this? First off, I totally agree with Al, but one of the things I think would be worth keeping in mind is, from my perspective, the government is generally not asking for AI. They want to see what's out there, but it would be like you as a homeowner that's having your house built to say, I want this house built with only table saws and jackhammers. AI is a tool. It enables a particular mission. So if there's a mission requirement that drives AI into the solution space, fantastic. But in general, they're not looking to acquire like a tool, a construction tool. They're looking to acquire a capability or a system. And differentiate between the hype and the marketing and what's actually under the hood. That is something that they generally lean on their FFRDC and national lab ecosystem to help them see through what's actually behind the curtain. But I just wanted to point that out, that while the government is interested in understanding what the state of play is in AI and how they could leverage it, in general, most program managers are just looking for a capability or a system.
Debra, can I chime in? It will be partially redundant, but I want to mention a kind of catechism or strategy that many academics use that could be helpful to answer this question. We start from a motivation, obviously, and then we define a problem statement. So the problem, this whole effort should be driven by the problem that needs to be solved. Then there should be a comprehensive investigation of what tools can answer that problem and what are the gaps. Now, the researcher, but considering the context of this question, the contractor, the provider of a service, should be able to demonstrate that there is a gap when analyzing the state of the art. And something needs to be done in order to bridge that gap. And here comes the innovation. So on the other side, there should be a vetting process where that service or that tool that is provided is comparatively assessed with the state of the art, so to show that it can solve the problem that previously was not solved, or it can solve it better. And so if you have that rigorous approach through vetting, that this is what we do to publish journal papers, for example, in a different field, then this is bulletproof, so to say. And that's what I would recommend the government to have a vetting process whereby you don't trust things face value or just by their names, but their capability to solve a problem and do it better than existing technology.
Debra, would you like more audience questions?
Yes, please.
Okay, so we have one here, and there's a few around this theme, and that's the idea of trying to get a sense of what are some of the up and coming important missions to test and prove AI in space. There was discussion about whether the compute components are space qualified. So what's the outlook for getting those up into orbit to test them at like a TRL level 8 or 9? What's the prognosis? Are we doing enough? And Debra, you can decide who this is best for, or somebody can just jump in and volunteer.
Yeah, who would like to address that?
Let me go ahead and start, because I'm thrilled. The whole space industry is blossoming with missions from VLEO, even suborbital, to lunar infrastructure, cislunar, and there's just a number of areas and domains where advanced algorithms and software, including AI, are again, people are eager to solve problems, hard problems, and I absolutely agree with Dr. D'Amico and Mike that what we really need is results, and results that advance existing problems as well as take on new problems. I mentioned lunar surface activities, everything from building out infrastructure, power grid management, navigating, to just health and wellness of astronauts, getting to the point where astronauts are not spending a large part of their time maintaining infrastructure, but actually conducting the science and research and exploration and commercial activities that we hopefully will be getting to on the surface. I think that's ripe for advanced algorithms and including AI. I do believe that I've been working space missions since '89, late '80s, including on console. If you look at autonomy levels, SAE autonomy levels, at best we hit level 3, maybe level 4 in some areas, but most of the time you have people on console monitoring satellites or constellations of satellites. We need to get just traditional kind of satellite operations beyond that. Similarly, focal planes that pull down massive amount of data, petabytes of data that, historically you might get analysts looking at an image, but now we simply can't do that. There's constellations of large format focal plane arrays pulling down imagery. I think, even traditional image analysis has to start and has been pulling down imagery with more impact, insight and actionable information. So there's quite a bit that of existing problems as well as new challenges that where we're going to be able to apply it, and it's actually an exciting time where this the confluence of these. Let me add one more thing, because Mike mentioned about AI in the hands of kids. Here in Silicon Valley, experimental self-driving cars have been around for about a decade. Although I wouldn't hand over a 2-ton robot to my kids. My kids ride their bikes to school every day. And there goes a self-driving car, whether it's Waymo, Nemerouf, Cruise, number of them. There's probably 24 self-driving car companies. So AI and AI-enabled autonomy is around us already. It isn't just facial recognition at the airports or other things. This is real robots, real machines moving around us and enabled by AI. What the promise in space is that we move a lot of that capability into the space architectures and domains. And just like here on terrestrial, I believe we do add a whole next level of capability, autonomy, quality of life with that capability. Over.
Okay, we got one more question here that we're gonna, I think, have time for. Given that space traffic management is a problem that's on our doorstep, it's knocking to get in, and we keep telling it, hold on a minute, but is there any value in space-based collision avoidance systems? The premise of this question is, given that collision warnings are typically received days in advance, would it still be beneficial to have these systems on board satellites rather than on the ground?
Well, I think it's unavoidable. So
Pardon me?
let me.
It's unavoidable?
It's unavoidable. I mean, this is what will happen. I mean, it's with the proliferation of space assets, we cannot rely anymore on a purely ground-based approach with all its delays and pitfalls. And as I mentioned, this is what, for example, SpaceX is trying to do, to push as much as possible these autonomous capabilities to the satellites, because they suffer huge delays in communication, for example, with Space Command. And there are also, I'm sorry to say, but some a little bit outdated approaches. I consider some that, for example, require knowledge about maneuvers that will be executed by a spacecraft with, over 3 days in order to produce this conjunction assessments are not compatible with autonomous spacecraft. And so I think it's unavoidable that space situational awareness will become a space-based, so will be complemented by space-based assets in two directions, both for the tracking and monitoring of space assets and for the autonomous collision avoidance. But I wanted just to briefly mention reference to the question before, that GPUs have already been flown in space. For example, the NVIDIA Jetson TX2i system on module has been used in space applications. And the NVIDIA Orin processor, for example, is getting qualified for space application. This is obviously the progress made by small space startup companies, which are less risk averse, and due to the low cost of these satellites, they can try hardware in space and check their survivability. So there is a COTS, a commercial off-the-shelf approach, that is showing promise in the qualification of GPUs in LEO, and not forgetting about Snapdragon by Qualcomm that is on the surface of Mars. So I am optimistic regarding the progress in the deployment of GPUs for space applications.
Yeah, and Dr. D'Amico, let me just, I don't want to beat up the government too bad. AFRL, the Air Force Research Lab, and NASA have been investing heavily in exactly that, right? Flying commercial off-the-shelf GPUs on the ISS and otherwise. And in fact, Aerospace, actually, the Aerospace Corporation, with guidance from the Space Force, is going to be putting up an on-orbit AI-enabled test bed where we're going to be running NVIDIA TX2s in a constellation to help accelerate industry approaches and mature the technology that demonstrates real results on a real-life sensor suite in space. So the government is investing. I am also highly encouraged by low barrier to entry to space and the government's continued investment.
And I would add that that the spaceborne computers from HPE on the International Space Station are also demonstrating AI applications in space. We're just about out of time. Are there any last comments any of the panelists would like to make before we do sign off?
Just appreciation for Space News and your leadership in always bringing out great conversations. Again, kudos to Stanford and Dr. D'Amico for organizing and sponsoring or organizing and running the CSER initiative. I think that's critically important, bringing the researchers in with industry in order to advance this capability in space. So kudos on both accounts. Thanks.
Thank you. And I've copied all the questions also. I'm sorry, did somebody have a comment?
I just wanted to thank Space News and you, Debra, specifically for this initiative. This is really great. And our sponsors of the CSER Research Center, Redwire, Al, thank you so much because you are an enabler of this, and Blue Origin.
I wanted to thank you as well. And I really like the composition of the panel. I think the future of bringing AI into space systems is all about a partnership between FFRDCs, academia, private sector, and government, because we're all going to need to figure it out together in order to get after this. So I really appreciate the thought put into this panel and the perspectives of everybody that we've heard from today. So thanks, Debra.
Thank you. Thank you all for joining the panel. And thank you to our audience for the questions, which I've copied to drive my reporting, because this conversation is still in the early stages, and we'll be watching this area and reporting on it carefully. So thank you, everyone.